All right, so today we're going to keep cruising with the sun and the solar composition, which is one of my favorite topics. I wanted to mention one thing. So a lot of people have been asking questions. People are concerned about the math in this class. And in general, I wanted to just talk about the role of math in astronomy and the role of math in science in general. And I want to talk about primarily the difference between a description and an explanation, right? So math is quantitative logic. What is logic? Logic essentially means that if you have a set of assumptions and you process them axiomatically, you basically say, if this, then this, right? Then you apply this, what we call logic, across the board, then you'll reach a conclusion that's hopefully useful to you in the end. This is what math does, except math can only do logic with quantities, right? So math can't really, philosophers play with logic equations in terms of ideas more. Mathematics just does quantities, so it's quantitative logic, all right? Now, that's really, really useful for describing the motions of bodies, describing the behaviors of everything from organisms to stars, right? It's really good for mapping the motions and doing it in a predictable way that we can look into the future and say, hey, our stars, let's just say our planet moves in a certain way. It moved that way yesterday. It's probably going to move that way tomorrow. And we can map that onto a set of quantitative logics that allow us to make predictions about the future. This is super useful for building stuff, right? This is why human beings are the weirdest animals on the planet, in my opinion, because we're able to do such things as make this classroom and make these screens, right, and gadgets. These are highly mathematical enterprises, right? Because we can parameterize our situation and we can build something that allows us to not actually have to understand the science of what's going on inside of it. That's what's critical about it. Think about how the first technologies were developed, right? Let's think about some caveman building a bow and arrow for the first time, right? Now, did that caveman sit down and draw out the differential equations for airflow and for, trajectory and speed? Absolutely not, right? And what's really funny is that we still develop technology the same way the cavemen did. We try stuff. It doesn't work, we change something about it, and we try something again. Mathematics allows us to parameterize those things that we're trying. We're going to change the length of the bow. We're going to change the tension of the string. And we can do those and check them off. And if the arrow is flying too far, maybe we lower the tension of the string, and we can parameterize that, and we can make these predictable assessments about what's going to happen when we make that change. And this is phenomenal. It's actually really humanity's greatest achievement, in my opinion, because it's allowed us to put our ideas on the table. And I think this is why scientists love mathematics so much. It allows them to put their ideas on the table, and everyone can look at it the same way, understand the assumptions that go into it, and then criticize it and hopefully improve it. Now, what's a little bit tragic is that, particularly in the discipline of physics, mathematicians have completely overwhelmed the discipline, and this happened in the last century, in the 20th century, and we're going to tell that story a bunch more. We're going to get into that next week in great detail. Now, the problem with mathematicians running the party is that science is actually a very different enterprise than engineering. It's a very different enterprise than mathematics as well, because in science, what we want to do is explain the cause of a phenomena, right? So, what does that mean? That means that if, we walk in and this coffee maker's on the floor and it's shattered to pieces, we want to explain how that happened, right? So, we can bring in a lot of math to describe how the coffee maker fell to the floor and how the structural components weren't able to withstand the pressure of the floor smashing into them and so forth. And that would be all well and good, but it wouldn't really tell us that, somebody, let's say Travis came in here early this morning and kicked it over. Sorry. Right? They're not going to be able to math can't do that for us, right? And so science comes down to mechanism. It's always about that mechanism. What was the actor that did this to this other object in order to cause the phenomena? This is a very, very different enterprise than engineering and mathematics on its face, okay? So what we're going to run up against over and over and over again here is that at some point in the early 20th century, there was a huge bifurcation between the mathematicians and the real physicists, okay? Prior to the 20th century, physicists were trying to explain everything, light, gravity, electromagnetism in general. They were trying to explain it with material actors, right? They had this substance that pervaded all of space that they called the luminiferous ether. And this was a foregone conclusion. This was absolutely how things worked. And people had different theories about it. Actually, some of the most venerable scientists who gave us the equations that we use today, like Maxwell and Faraday with electromagnetism, they all tried to understand and represent their ideas in terms of the way that this medium was capable of conveying light and gravity and so forth. So something really interesting happened, though, because around the turn of the century, at the end of the 1800s, people went looking for this substance and they couldn't find it, okay? Around the same time, a little bit later, people started trying to describe reality. Well, actually, I think as a product of the fact that they couldn't find it, some really clever mathematicians started thinking, hey, what if we just ignore that substance? What if we just try to describe reality in terms of one actor in relationship to another actor? What if we did that for the whole universe? What if we just made our entire description of reality relativistic? What if we made it based on how things are with relations to other things? And this was very successful. It actually gave us a really, really powerful predictive description of nature, of how things are going to unfold. But it absolutely kicked the question of what's causing those events to happen out of the arena completely. So we'll keep revisiting this over and over again. But I think the best way that I can describe it to you was something, I can't remember the author, maybe I can post this on Moodle. But I read this really, really wonderful philosophy paper by this Greek philosopher. And probably can't remember his name because it was really hard to pronounce. But he was basically made this analogy. He said, let's say there is a man on stage and he's sawing a woman in half at a magic show. What the relativists would do, and what mathematical physics in general would do, is they would say, hey, let's look at this sawing behavior from every angle. Let's get a picture of it from over here, from over here, from over here, and we'll construct a three-dimensional representation of what's happening on that stage. And that's well and good. That's actually the best way to start to analyze something and try to figure out what's going on. The problem is that they stop there, right? They stop at the point of describing exactly how everything is happening. They don't go so far as to explain the fact that, oh, the woman pulled her legs up into the box, this thing was sawed in half. It's actually a magic trick, right? And so much of nature is a magic trick. And especially if you go back thousands of years ago, everything was magic. All of the stars, the sun, everything was a supernatural entity. And there's merit in that too, and I'm going to talk about that a bit today too. There's merit in the way that people used to view these things. But the problem is a lot of the, I saw a paper the other day that came out, I think in Nature, that said basically our rate of scientific innovation has completely stagnated. There's very little progress being made. There's incremental progress. There's a lot of reasons for that. We say you go to grad school. I don't know if any of you are even going to go into science, but if you go to grad school, your advisor will probably say, hey, I'm working on this project. There's a little piece of it that I'll hand over to you, and you can take it a little bit further. And what happens is people do that, and they think, okay, this is a good way to learn, and it is, except then they end up doing that for the rest of their career, forever and ever and ever. And everybody is just working in these tiny little niches on these tiny little problems, and they're advancing the descriptions, right, the mathematical representations of these behaviors with increasing accuracy, which is super valuable to technology. And where do you think all the funding comes from? From technological application, right? So basic science that's concerned with how things actually unfold is not a well-funded enterprise, okay? So all these things are kind of understandable, but I want you to try to keep those two ideas in your head as we go through this course. And when you try, you're going to see me up here many times ranting about the material significance of different events. And, you might say, well, who cares, right? Like, who cares if we don't understand how gravity works on a material level, or if we don't understand the material composition of the sun, which is what we're going to talk about today. And I would say, you're right. In the short term, it's probably not that big of a deal. We can continue to incrementally improve our technologies. But in the long run, I'm talking if we want to do things like harness the power of the sun on Earth, if we want to be able to have clean energy, if we want to be able to travel to other star systems, we're going to have to make some huge paradigm shifts. And we're not going to be able to do that if we don't understand what gravity is, if we don't understand what the sun actually is in structure, in form, what it's made out of, how it's accomplishing this. There's no doubt that the sun is fusing atoms together. The question is, how is it doing that? The understanding we have about how it's doing it isn't really working out for us on Earth right now, right? Despite what you'll read in the headlines, the incremental progress is not leading towards an actual power solution. And so these things really do matter. And there is a terrible confusion between science and technology. And most people consider them the same thing, but they're not. And sometimes science can inform technology, but technology is certainly comfortable with moving on without the science. That's not a problem at all. And mathematics, in its own art form, is completely divorced from reality. All it does is take some axiomatic assumptions and process them logically. So if we assume blank, then we can just move on and make a mathematical theory out of it. Which also brings up the point, what is a theory? Somebody asked me this earlier. Well, the word theory is one of the most abused terms in the whole party, pretty much. Because theory for a mathematician means a very different, or for an engineer is a very different concept than a theory for a scientist. A theory for an engineer is just a set of, or a mathematician, is just a set of equations that it makes makes predictions that are reliable. A theory for a scientist actually involves mechanism. What are the actors doing to one another, like I said? Who kicked the coffee off the table, right? It's very close to forensics, actually, basic science. Okay, so any questions about that? It's going to keep coming up over and over and over and over. But let's get on to the sun. So one thing I wanted to mention, we ended on something like this graph. We were talking about the cycles of sunspots. And I mentioned that it was highly correlated to climate on Earth, actually, which is maybe quite startling. And this was known for a very long time. I did want to mention that there happens to be, there's no really good explanation for what would allow the sun. There's nothing you're going to find in a textbook that's going to tell you why the sun activity is causing, or why the decrease in solar activity is causing temperatures to fall. Your textbook makes the point that one possibility is that that volcanism could be related to it. So that when the sun is actually, the sun is actually influencing the seismicity on Earth, which is leading to volcanism, which is putting aerosols into the atmosphere. Maybe, right? We don't actually know. This is a huge topic for research, though, and there's a lot of people who are starting to tear into it. But I think I don't have anything else to add to that. So the majority of today's talk is going to be about the history of how we came up with the ideas that we have about the sun. I want to spend a great deal of time talking about the evolution of the idea that the sun is a big burning ball of gas, right? Which to me is the most problematic thing in solar physics right now. Other people might disagree, but I've talked to a lot of astrophysicists. I've talked to people at NASA who are leading the teams that are building the probes and going to the sun, the edge of the sun, right? And they very much do not have answers to these questions. And that's really exciting, right? That means those are things that maybe one of you will get into one day. and nail it down. So anyways, let's go back to the beginning. So what do we have here? This is actually a Bronze Age sculpture that depicts the sun being carted across the sky. And the sun has always been a central fixation, right? It's literally the life-giving entity, right? Without the sun, you can't grow plants, you can't see. And it has this strange regularity to it, too, that people noticed almost immediately, which was comforting, actually. Because if you can make predictions about your world, you're in a much better situation than otherwise. I mean, think about, do you guys have pets? You probably have pets. I have a cat, right? Her name is Mingus. And she's got this strange attention span, right? If there's ever like a bang on the side of the room, right? She's like, oh my God, what's going on over here? Any little thing that happens that changes in her environment, she's completely freaked out about because she doesn't have a model for the safety of the room. She doesn't have these models of predictable sets of behaviors. Like, look at you guys. You all come in this room, you know what to do. You sit down in the chairs, right? Nobody's like worried about their neighbor like coming over and sticking them with a pen in the side or something, right? Like, people know how to behave, right? And where did you learn that? It's not totally clear where you learned that, but it is baked into the system of being a human on Earth, right? You park in the parking lot, you don't park on the lawn. Like, there's things you do, and of course there's consequences for misbehaving, but generally speaking, we do these things because these systems of order and regularity have been set up over thousands, maybe millions of years. And the sun, I think, was one of the first celebrations of that concept of order. Because, without order, it's just complete madness. You have to be like my cat, worried about every little sound that's happening. You have to be worried about every little, where am I going to get my food? Are the rains going to come this year? When is it? Is it winter? Is it summer? These are really important things to celebrate, especially in the primitive cultures that were very much concerned with survival. Not that we're not concerned with survival. Oh, come on. So some of these earliest representations come from the Bronze Age. I wanted to read you guys a little passage. So there's a book that I used a bit last semester. I highly recommend this book. It's called Native Science by this gentleman. And most of these references come from the Navajo tradition. We obviously have our own native tradition up here in Oregon. I couldn't find any writings from them, so we're going to be stuck with the Navajo. But I wanted to just give you a glimpse of, in their own words, what the sun meant to this culture. Kate writes, "First man and first woman brought the energy of the sun, moon, and a crystal star from the first world. In the second world, Coyote, first boy, and first girl were created, and together they brought the knowledge of heat and light from the clear crystal to the fourth world," this is our world, "all of which was eventually used to produce the sun. The Holy One decided that the sun, considered to have male characteristics, would provide order to the days and seasons. The seasons are recognized by the location of the sunrise." So, this is exactly what I'm talking about before. The sun brings the order to the situation, and order is absolutely essential to everything that we do. Honestly, in your own lives, right? If you don't have order in your own lives, you're never going to get anywhere with anything you're trying to do, right? I mean, if you don't have your bags laid out and stuff, you're not going to make it to class on time, right? If you don't have your assignments laid out in a calendar, you're not going to get them done on time. If you'd get one thing out of college other than making a bunch of friends, figure out how to organize yourself so that you can get things done. That's really the only thing that matters in life, actually. It doesn't matter whether you can, well, it doesn't matter anything else, really, right? If you can get ordered, then you can do all right on the tests. If you can find a way to program a little bit of time here and there, these are essentially what people were celebrating when they made these deities out of the stars and out of the sun. So I don't want you to think about them as just like primitive dum-dums, right? These are people who recognize that this is one of the most essential aspects of human behavior, and they celebrated it through the stars and through the sky. And I think it would be a great disservice to just think of them as superstitious, silly people, because it's not like that. And honestly, if you look around the world today, especially in America, we've very much moved into this rational landscape. We don't have, religion is less and less popular all the time, and perhaps for good reason. The churches are corrupt, they do terrible things. There's lots of reasons to not like religion. But when we moved away from religion, we very much lost our ability to celebrate purpose and celebrate our place in the cosmos, right? And it's not clear how we find our way back to that now that we've essentially said that that's not an interesting mode of approaching the subject. So, I think there's a lot of wisdom from our ancestors that's maybe treated as a bit primitive when in fact it's actually quite prescient. Something to think about anyways. All right, so some of the first astronomers were actually in Babylon. This is a Sumerian tablet, I believe. And this was, some of the first real records came from the first millennium BC. So this is, the 1,000 years prior to 0, okay, which is arbitrarily marked out, around the time of Christ, right? This is where we get this. And of course, these calendars were set up by the church, right? That's why we have everything marked from this religious moment. So 1,000 years before the church got involved and set up the timekeeping system, the Babylonians were watching the stars. And what's really interesting is the Babylonians actually had a whole class of people that lived on one part of town that were the astronomers. They weren't particularly treated well either. I wouldn't say they were a slave class, but they didn't live in palaces, but they were important. And they were essentially a servant class that were brought to the palaces to divine what was going to happen next. And I think this is really important because in almost every culture you see that whoever is able to, like if you're a leader, what's the coolest thing you can do other than saying what's going to happen tomorrow? I mean, I'm going to follow the guy who knows what's going to happen tomorrow, right? So this is a pattern you see in every single culture, from Mesoamerica to the Far East. Every culture, there's some class of people that are able to do that divining. Yeah?
Well, isn't this astrology and not astronomy?
Yes. So there was no difference originally, right? Astrology in the modern sense, and we talked about this last semester, but in the modern sense, astrology is really this idea that the moment of your birth was influenced by, trying to scientificize this, influenced by the gravitational interactions that you experience, the positions of the stars and the planets, right? And this is a whole different matter. I think that these original people were actually closer to astronomers in that they were watching the position of the stars and they were making predictions about where they would be tomorrow. They were able to predict eclipses, which was, I think, rather stunning for the people. If you're a king in Sumeria and you can say, hey, tomorrow the sun's going to be blotted out. I mean, everybody's just like, right? It's just unbelievable. I mean, oh my, how did he know that, right? And it turns out that, of course, eclipses are very predictable. If you have just taken some records for a while, you can actually come up with mathematical models that describe regular behavior, right? So you start putting all these different variables into your equations, and you can actually make these incredible predictions, which basically look like a magic show. So yeah, there's some subtle differences. I mean, one of my favorite things about astrology is that, is anybody into astrology in here? All right, a couple, okay. So the funny thing about astrology is that if you open like your horoscope to like a newspaper or something like that, right? It's like, your birthday is here. My birthday is in March, so it's like, oh, okay, you're an Aries. So I went through my whole life, I'm like, I'm an Aries, Well, it turns out that the position of the stars has actually changed in the last 2,000 years since this all went down. That makes me actually a Pisces, which is really funny. So I was reading the wrong column all along. It was right somehow, I don't know. Okay. Sorry, I won't pick on the astrologist. It's an interesting idea, I do think that, and we'll get into this next week with relativity, I do think that the position of the stars and the planets, every single piece of matter in the universe really does affect every other piece, right? And we'll talk next week about how Einstein derived his principle of general relativity based on this idea, which was an idea that Ernst Mach had, actually, which was like something like, hey, if I spin my arms around like this, why do they fly out to the sides? And Mach was like, well, I think it's because your arms are connected to everything around you. And that's actually a really brilliant insight that I think can be further developed in the future. So anyways, I think that the basis of all of that is sound. I don't think anyone's actually been able to ever show astrology in a scientific sense has panned out. Generally, the predictions that it makes are very blanket and heartwarming and sort of work for anybody. And you can open up 2 different newspapers and get 2 different sets of predictions. So one's like, stay in today, and the other one's like, go outside and make friends. So, yeah.
How does the Chinese zodiac signs?
I have no idea, I'm sorry. Yeah. Anybody Chinese zodiac signs? Are they related? Somebody, you had an idea?
About how they were derived?
Are they related to the Western Yeah. Not at all. Different, I mean, certainly different. So the zodiacs are essentially, the zodiac is essentially the constellations that are in our plane, in the ecliptic plane in which all the planets orbit the sun in. And of course, I'm sure people in the East, I know for a fact that people in the East came up with different representations. So, people in the West based their interpretation of what the constellations look like on their own myths, right? But the people in the East have totally different myths. And we spent a lot of time last semester. I don't know if anybody has the chance to take 112 next fall. Take that, because we'll go through all these myths in great detail. But they're very different stories. What is kind of fascinating, and I'm kind of getting off the rails here, is that the myths do share a lot of overlap. In fact, especially when you look at things like Venus, it's kind of creepy. Like the people in the West, the people in Mesoamerica, completely unrelated, no contact, they have really similar stories for a lot of these star systems. And I don't know, I don't mean to say it's creepy like it's some supernatural thing. I just mean that there are natural stories that live inside of each one of us, right? There's things that play out. There's behaviors that play out. There's these ideas of betrayal and loss and defeat and triumph that happen no matter what culture you're born into. They're very human. So it doesn't surprise me too much that people are going to come up with these same representations over and over again, and that they're going to play them out in similar representations. Venus is a really amazing planet. It does this strange thing where it appears in the morning for about not quite a year, but several hundred days. Then it disappears for like a week, and then it appears in the evening for another couple hundred days. This is very, very strange. I mean, this puzzled everyone, but it lends itself naturally to these sort of underworld stories, right? Of some hero going into the underworld and conquering some villain and coming back out, right? And this is of course the story of your life, pretty much, right? I mean, you're going to have troubles. You're going to have to defeat something. Something is in your way. You have to overcome it, and then you're going to rise from that. This is a very primitive, archetypical pattern that plays out. What else do I want to say there? Okay, so the next people who came along and essentially inherited all of this Babylonian ideas were the Greeks. And this is, I'm tracing, of course, the Western tradition, which is just making sure you guys all realize you're in the West right now. So we have to trace our ideas about this from the textbook. I'm trying to get back to where they came from, right? So the West had virtually no contact with the East for all of history, certainly. There's a few anecdotes of some people meeting up on like the steppe. There's some talk of like these people across the mountains in the West, but they were very isolated. And so the stories very, very much depart. And honestly, especially last semester, I was trying to research a lot of the Eastern astronomy traditions, and it's very difficult if you don't read Mandarin, if you don't read Japanese. There's not a lot of interest in sharing those things with the West. There's still quite a divide, which is really interesting. Okay, so the Greeks. So, there was a Greek scholar named Anaxagoras who was the first person to really write about anything remotely close to the science of the sun. And what's really fascinating is that Anaxagoras reasoned that it wasn't actually the chariot of Helios. it was actually a giant ball of metal that was burning, which is like, because that seems to be really close to where we're at right now. I talked to you before at the beginning of last lecture. What is the consensus idea of the sun? Well, it's a burning ball of plasma. What's a plasma? Well, it's a gas. Sometimes it's a liquid, sometimes, but it's definitely metallic, right? Definitely has conductive properties. And there's reason to believe that there's conduction bands in it, very much like a metal. So this was the first idea that was ever written down about the sun. Turns out to be actually really, really close. And what you're going to see today is people went all full circle. They tried on every possibility that they could possibly, that they could ever conceive of. And they ended up very much back close to that at the end of the day. And there's still some details to be ironed out about that. So that's really interesting. Who else? So what? By the way, what did they do with Anaxagoras? They imprisoned him for heresy. Right? And it's funny, we laugh because, that sucks. He had a great idea. It's not that different today is the funny thing, right? And I mean, it's very, very difficult to move a mountain the size of the canon of science, right? If you have a new idea, you will almost certainly be laughed out of the room for many years before somebody takes you seriously. This happens over and over and over again, and we went through a number of these paradigms last semester with the planets. People come up with the right idea, and nobody cares, and it's heartbreaking, and I deal with these people every day, right? I run a podcast where often, we talk to mainstream scientists, NASA people. We also talk to complete lunatics who have cool ideas. I don't know if they're right or not, but we talk to them. And they're almost all completely heartbroken. I had this great idea. I thought the world would be so excited for me. And they all are basically like, get out of here. Like, we don't need your new idea, right? It's very, very, very difficult and very tragic. Actually, being a groundbreaking scientist, even if you're in the academy, can be very heartbreaking. And I don't have time to regale you with stories of that, but I have a number of them. They'll come up over and over again. Okay, so, this guy was sentenced to death for heresy. Actually, he ended up getting out of that by the intervention of Pericles. Later, a little bit later, so 400 BC, 3rd century BC, this dude named Eratosthenes came along and did a number of really magnificent geometric calculations that allowed him to basically determine the size of the sun, distance to the sun, size of the earth, and things like this. We went through them last semester. It's a really cool story. And actually, a guy who was much more popular than Eratosthenes named Ptolemy came along and said that Eratosthenes was wrong, gave a whole new set of calculations, and those became very popular for about 1,000 years. Turns out Eratosthenes was actually right the whole time. So people were operating under Ptolemy's system for 1,000+ years, completely wrong calculations about these distances and sizes. Ptolemy also is famous for having completely failed on the model for the solar system, right? So Ptolemy thought that the Earth was at the center and everything went around us, which is totally reasonable, actually. If you look up at the sky, it does seem to be the case, but it's wrong. And so this is another wonderful instance of something being absolutely predictable, regular, even makes sense when you go outside and look at the sky that it's revolving around us, but it's not true. It's not the case. Yeah?
So it seems like a recurring theme is as we begin to lift the veil of mysticism, it is rejected.
And you see that today more and more, right? And I think this is wonderful, though, right? Like, I unlike a lot of people that you'll read about, I'm not sitting here saying that we know nothing either, right? Actually, we know more and more in terms of observational evidence. Our mathematical theories are tighter and tighter, and we'll talk about how Einstein improved on Newton, but they definitely don't necessarily concern themselves with the cause of phenomena so much. And this is where things kind of go off the rails. So yeah, if you look at the headlines, you're going to see all sorts of headlines today that are completely mystical, right? And I think that's understandable, especially in a world where we've basically deleted God from the equation. It's like people look to science to explain the universe to them at this point. the problem is science isn't really equipped for that. It's not really equipped to tell you how to live, how to behave, what's going to happen when you die. Why is this place here? These are the existential questions that science has no chance at, right? I mean, it will try. There's always going to be someone who's going to stand up and say, oh, who has a PhD is going to tell you, this is my theory. They might even have fantastic mathematics to back it up. But these are difficult questions for science to answer. And so I think that's a huge problem for humanity in the next generation is like, how do we come to a point where we can celebrate the virtues of existence without getting some church involved in the matter? I don't know if that's possible, but I like to think it is. All right, so most of the history of observing the sun concerned these sunspots. And honestly, all the way up through the end of today's lecture, when we look at the history, it's going to revolve on what the heck sunspots are. Because they were very predictable, but people were trying to understand them in terms of what the sun was made out of. So now remember, sunspots are this weird phenomena in the photosphere of the sun. That's its effective surface. That's the surface we see, where there's temporarily these little dark spots in the surrounding area. And today we think of today the consensus idea is that they're essentially these magnetic tangles that sort of pull the place apart locally. And these magnetic tangles can unfold and release pieces of material that fly out and hit us on Earth. They call them coronal mass ejections, right? Sometimes you get little flares, right, where there's huge bursts of light released, very powerful X-ray light that's quite damaging. So sunspots, all right? So they were actually observing sunspots during the Han Dynasty, which was somewhere around 200 BC. There was also a great deal of sunspot observation 1,000 years later in the Islamic Empire. So the early Islam was obsessed with math. They actually gave us algebra. They have done incredible record keeping, and they made great records of these sunspots. And they were very accurate. It wasn't until the 17th century, so the 1600s, that Galileo was actually able to see that sunspots weren't some thing going by the sun as it was originally thought. They thought, oh, maybe the sun is surrounded by these clouds that go by or something like that. So Galileo was the first person who said, I think those things are actually smaller than the Earth. They're not planets. There's something else going on there. 1 second. So let's keep going. You'll notice that 1,000 years went by too, and not much happened. We call those the Dark Ages in the West, which we're not particularly proud of. And they were called dark for a good reason. And actually, that brings up another point. Dark, when you see the word dark in science headlines, it generally means we don't understand what's happening here, right? So we'll deal with dark matter, dark energy, black holes. We have a whole week devoted to these dark ideas, right? But they are the most nebulous, and they are going to be the most readily mystified by the popular media, too. So I hope I won't break any hearts, but I'm not, when it comes to science, I'm not much of a mystic, right? And so I'm going to try to give material explanations for those phenomena as we go through, because I think that's really important. All right, so this is Newton. Newton is one of the first deities of modern science, right? It's almost unimpugnable. Newton, of course, came up with a lot of the ideas that we have for optics and gravity. He essentially gave us the gravitational equations that we still use to go to outer space at this point. We have more precise descriptions now with relativity, but we don't really use them for that kind of stuff. So Newton did a lot. And Newton started actually for the first time breaking the sun's rays into their constituent colors, right? And I talked about how these prisms work last time. This was huge. So Newton came up with this idea that light was comprised of all these different, white light in particular, and the light of the sun is actually a rainbow of different colors. And at this point, I want to flip over and talk about the nitty-gritties of what happened after Newton. So as soon as people discovered that light that the sunlight had all of these different colors. They immediately started tinkering with things on Earth and figuring out how you get these colors out of it. So my dear friend Pierre has done a fantastic historic analysis of the solar composition. And I'm essentially, all the stories I'm going to tell you for the back half of this class are going to come from Pierre's paper. This is a fantastic paper. I'll try to put it in Moodle later. But I want you guys to hear the stories of how these things happened in the words of the people who were actually studying it at the time. So I'm going to read you guys some really interesting passages. But basically, I want you guys to understand how we worked our way to this idea of a gaseous plasma, and who are the people who got involved in that, and when did we come up with this idea that the surface of the sun was just an optical illusion, for instance? And it comes down to essentially there's 5 pillars that we stand behind today, or consensus science stands behind with regard to the structure of the sun. And those are the planetary formation hypothesis, which is called Laplace's nebular hypothesis, which is an idea developed in the 1700s that we essentially have today for how a solar system is formed. It's a little bit different, but it's essentially the same idea. Then this guy named Helmholtz came along and talked about the contraction of big, nebula, how the contractile process leads to the birth of a star. The idea of critical temperatures, so how gases how matter behaves under different temperature and pressures. That was a brand new science in the late 1800s, so that played a huge role. Kirikov, who we talked about last time with the black body radiation and his formulation of thermal emission and how that works, how hot things give off light. And then finally, this discovery that gases under pressure modified the way that they gave off light. And so those are the 5 big ones. But let's start at the beginning. So the first idea, so we talked a little bit about the Greeks. There is some thought that even prior to the 3rd century BC, there was this guy named Thales who posited that the sun was a solid body. But very, very little work was done on the composition of the sun until the 1700s in Europe. And there was a great scientific community at the time, letter writing. There was no such thing as career scientists, right? So these are all basically rich barons or people who just have a lot of time to kill. Almost all of the scientists of this day were either rich and men of leisure, or they had a job, like they were a lawyer or a doctor, something like that, and they just played with astronomy and light and chemistry. They just did it for fun, which is really interesting because they weren't really driven by this careerism thing, and there was a lot more congeniality amongst them. There was a lot of people just sharing ideas in personal correspondences, something that you would almost never see today.
Sorry, I haven't seen the roll sheet.
Oh, who's got the attendance?
I don't know how it. Did you guys do
Did it get lost?
I think it just skipped this round.
Who has it?
I don't think it came down this.
Oh my goodness.
It's still up on the desk.
Really? Okay, interesting. Chaos. All right, can somebody, if it's on the back desk, can you look for me? Did it make it back there? It did. All right, send it back down this row, and then we'll get it up this one. Thank you for pointing that out. We'll figure it out by the end of the semester, I promise. All right, so in the 1700s, there was a gentleman who came around named Lalande, who was a Frenchman, and he actually said, no, I think that the sun is actually a fluid. And he wrote a bit about Galileo. He wrote this about Galileo. He wrote, Galileo, who was in no manner attached to the system of incorruptibility of the heavens, thought the sunspots were a type of smoke, clouds, or sea foam that forms on the surface of the sun, and which swim on an ocean of subtle and fluid material. Galileo continued, I am led to this belief primarily by the certainty I have that the ambient is very tenuous fluid and yielding substance from seeing how easily the spots contained in it change shape and come together and divide, which would not happen in a solid or firm material. So fair enough. Galileo's like, look, the surface of the sun is changing all the time. It's probably not a solid ball of metal or something like that, right? Okay, there's problems with that though, and people are going to fight about it. Galileo also, by the way, he says, I'm not really attached to my ideas. He says, For I am very sure that the substance of the spots could be 1,000 things unknown and unimaginable to us, and that the accidents that we observed in them, their shape, opacity, and motion being very common, can provide us with either no knowledge at all or little, but of the most general sort. Therefore, I do not believe that the philosopher who was to acknowledge that he does not and cannot know the composition of the sunspots would be deserved any blame whatsoever, which is really interesting. So, we'll see this. There's different guys in this story, who have different levels of modesty about their opinions. Unfortunately, in the culture that we're in today, usually the people with the most confidence and the loudest voices and the biggest microphones are the ones you're going to hear about. And so, not a lot of room for modesty these days. So, yeah, come on. Let's keep going. Come on. Computer's struggling. All right. Nope. There's a bit of a lag. Come on. All right. Nope. One more. So by the middle of the 19th century, engineering was king, right? People were coming up with ideas about thermodynamics. People were starting to think in a more mechanistic fashion about what was going on. And this is really when all of the progress happened. This is when all of the debates that we're really concerned with here started to unfold. So one of the first premier astronomers to really concern himself with the composition of the sun was a French dude named Arago. Okay, now Arago was mostly famous for working with Fresnel, who gave us essentially the experimental evidence for the wave nature of light. And so the two of them were essentially, already famous for this. And Arago after he was quite famous already, he turned his attention to the sunspots. He had this to say: "Many conjectures have been offered in explanation of these spots. Some have supposed that the sun, from which so vast a quantity of light and heat is incessantly emanating, is a body in a state of combustion, and that these dark spots are nothing else than scoria floating on its surface. The faculae, on the contrary, they suppose due to volcanic eruptions from the liquefied mass. The grand objection to this hypothesis is that it does not suffice to explain the phenomena. It has not obtained admission among astronomers." Fair enough, nobody buys it. "The opinion most in favor in the present day regards the sun consisting of an obscure and solid nucleus enveloped by two atmospheres, one obscure and the other luminous. In this case, the appearance of the spot is explained by ruptures occurring in the atmosphere and exposing the globe of the sun to its view." So, sorry. Goodness gracious. All right. So, another guy came along, William Herschel, who essentially, actually Herschel was ahead of Arago, but he wasn't as famous. And he essentially said something that goes as follows. Actually, this is written by his son, who wrote up a lot of his ideas. Speaking of his ideas with regards to the sunspots, while it agrees with that an aggregation of the luminous matter in masses of some considerable size and to some degree of consistency, suspended or floating at a level determined by their gravity in a non-luminous fluid, be it a gas, vapor, liquid, or that intermediate state of gradual transition from liquid to vapor, which experiments of Gagnard de la Tour have placed visibly before us. So people were starting to come up with this idea that there might be another state of matter in play, which is really, really, really interesting. This is the first time. What happened next is Kirikov showed up. And Kirikov had all of his work was concerned with black bodies, and he worked with Bunsen, like we talked about last time, on actually reproducing gas lines that tell us the elemental composition based on the light that's emanates. They burn substance. They see what colors come out of it. And so Kirikov was really at the front lines of understanding what light can tell us about the material composition of something. Kirikov had this to say: in order to explain the occurrence of the dark lines in the solar spectrum, right, these are the gas lines. Remember, the sun is a rainbow of color. It has these black lines across it, which correspond to the atmosphere, how the atmosphere is taking light out. In order to explain the occurrence of dark lines in the solar spectrum, we must assume that the solar atmosphere encloses a luminous nucleus producing a continuous spectrum. This is the black body, the brightness of which exceeds a certain limit. The most probable supposition which can be made respecting the sun's constitution is that it consists of a solid or liquid nucleus heated to a temperature of the brightest whiteness, surrounded by an atmosphere of somewhat lower temperature. This supposition is in accordance with Laplace's celebrated nebula theory, blah, 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 which we'll talk about. This was huge, right? Because Kirikov was one of the most respected scientists in his day. And he was actually the first person who really squared up the mathematical formulations of the relationship between temperature of a heated body and the rays, the wavelengths that you get out of that. So people took him very seriously. This guy named Magnus came along, who was also, he basically, Magnus took Kirikov's ideas and essentially deleted the idea that there should be any material structure to it. Magnus wrote this. He says, this is, I forgot to even tell you about Magnus's work. So Magnus did this really interesting experiment where he basically found that if you burned condensed matter, so actual like pieces of material, molecular material, if you burned that in a flame, you actually got a much brighter light out of it than you would otherwise. This is quite interesting. Magnus wrote, "My studies demonstrate that gaseous bodies emit much less heat radiation than solid or liquid bodies, and that, by consequence, one cannot suppose that the source of solar heat resides in a photosphere composed of gas or vapors." Lord Kelvin, another very prominent thermodynamicist of the time, comes along, and he writes, "It is, however, also possible that the sun is now an incandescent liquid mass radiating away heat, either primitively created in its substance or, what seems far more probable, generated by the falling of meteors in past times with no sensible compensation by a continuance of meteoric action." So this theory held for several decades. Lord Kelvin was super famous. He was like the Neil deGrasse Tyson of his time. He said that the sun was heated because there was meteors crashing into it all of the time. And people were like, yeah, that sounds like a great idea. And they didn't see this happening, but they couldn't figure out how it stayed warm, right? So these are some of the debates that were happening at the time. Lag, having a hard time changing slides. I'm sorry, guys. Okay, there was a really interesting guy who came along. There's a guy named Herbert Spencer. And Spencer was the opposite of Neil deGrasse Tyson. I'm trying to think of somebody this guy could be like today. He wasn't a trained Oxford astrophysicist. He was a natural philosopher. He had really, really distasteful ideas about the application of Darwin's ideas to race and to social evolution and things like this. People didn't like him in the academy, basically. But Spencer had some good ideas about the sun, actually. And I want to read you a couple of Spencer's quotes, because although Spencer, even if you go to Wikipedia today and you look up Herbert Spencer, you see everything about him. You will never see anything about his astrophysical compositions. He has been written out of history, which is a really tragic thing. But I think it goes to show that if people don't like you, you're not going to get anywhere. This is what I mean about science, right? It's not just about having a good idea. It's also about working with people, making a better place, right? Anyways. So Spencer threw up some ideas that were a pretty dramatic departure from what we've seen so far. He was very, very concerned about this idea that the sun had such low density, right? And we talked about this a bit last week. And this was the first time that this issue had been raised. He wrote, the average specific gravity of the sun, which is density specific gravity, is about 1. The more legitimate conclusion is that the sun's body is not made up of molten matter at all, but that it consists of a molten shell with a gaseous nucleus. The specific gravity of the sun is so low as almost to negative the supposition that its body consists of a solid or liquid matter from center to surface. So the sun, we can calculate density if we just know the radius of something and we know how much mass it has, which we gather from the gravitation. This was a huge problem, right? And I think this is really when the birth of the gaseous sun happened. The problem was that they were actually basing their ideas on the density of objects that we find on Earth, right? Like metals and things like that we have around here. Iron, right? Earth has a tremendous amount of iron. It's very dense. So how could the sun possibly be made out of something other than a gas? There's nothing else that could be so rarefied, right? This is interesting. And I think that Spencer's idea of a bubble, right, because he still had to rectify the idea that black body radiation, this beautiful spectrum that we see from the sun, comes from a solid object. We'd never, ever, ever on Earth have been able to take a gas or even a plasma and make a continuous spectrum, make a rainbow when we split its prism. Gases and plasmas always give off discrete lines. And so he rectified this by saying, well, it's a bubble. It has a shell that's solid-ish. It could be liquid, I suppose, too. And then in the inside of it is essentially full of gas. Now, there was problems with this, too. Namely, the biggest problem was people started saying, hey, if it's gas inside and we have these holes in this shell, we should be able to see right through it and see the other side of it, right? Gases are transparent. So, I'm going to skip Father Suchi a little bit. I do want to mention that there's a gentleman who was, yes?
Don't sunspots mirror each other, they lay to the opposite side of each other? If the gas was transparent, wouldn't you just be seeing deeper into space?
That's exactly the idea. Yeah, that's the problem, right? And the opacity of the sun is a really interesting issue, and we're going to build on it more next week, because the story that we tell ourselves now of how that works is very fascinating, because we have this story that the light bounces around for millions of years before it reaches the outside. And so that under sufficient pressure, that opacity begins to emerge, right? Now, the problem is we can't do that in a laboratory for whatever reason. It's a completely theoretical idea, but it forms the basis not only of all of astrophysics, but of cosmology as well. And so this is the stories that we tell ourselves about our place in the universe. It forms the basis of fusion technology, right? These are really important ideas, right? And I myself am not persuaded that these are compelling arguments yet. They are arguments, and we will definitely examine them. But they're very convoluted, and they're not based on experiments on Earth, which troubles me greatly, right? All I know is that when I heat a metal up, it looks like the sun. When I heat up a gas, it doesn't look anything like the sun, actually. So now the sun certainly has a gaseous atmosphere. That's not what I'm talking about. I'm talking about the photosphere, the surface. We call it the surface. So there was a gentleman who came along who had a little bit more street cred. His name was Suchi. He was actually I think he was a Jesuit priest. Could be wrong about that. He was a priest of some sort. Suchi solved this problem because, of course, it was brought up very early that, how's that attendance going, by the way? You got it still? Do you want to get this whole row first, and then we'll get that row? Yeah. Everybody in this row's got it? You guys didn't get it yet? Are you write your name then. You all know how to spell your names. Okay, so Father Suchi came along and he said, look, it can't be a solid because that doesn't, how are we going to get bubbles in it if it's a solid? So Suchi had this really interesting idea that there was actually a fine dust that was essentially of condensed matter that was woven into it. Let's read you a little quote from Suchi. Regarding the photosphere, he says, indeed, this appearance suggests to us what is perhaps a bold hypothesis. As in our own atmosphere, when it is cooled to a certain point, there exists a fine substance capable of transforming itself in itself in fine powder and forming clouds in suspension. Water transforming into so-called vesicular vapor or into small solid icicles. So, in the inflamed solar atmosphere, there might be an abundance of matter capable of being transformed in a similar state at the highest temperatures. These corpuscles in immense supply would form an almost continuous layer of real clouds suspended in the transparent atmosphere which envelops the sun, and being comparable to a solid body suspended in gas, they might have great radiative force of the calorific and luminous rays than the gas in which they are suspended. So this is Magnus's idea, right? Things actually get brighter when you dissolve these powders in the gas. All right, now what happened? Kirikov actually was the one who came back and said, hey, if there's gas inside, you should be able to see right through this thing. That doesn't make any sense. And he got in a big argument with a lot of the people of his day, and it kind of ended frustratedly with nothing really happening. But Kirikov again pointed to his black body experiments. He said, guys, solid liquid bodies give off black body radiation, gases don't. What's going on? So somebody came along. I'm waiting for my slide to load, get these names right. The next person that came along said, okay, it's all right. The thing is just such dense gas inside that when light is emitted, it's immediately refracted off of another atom next to it, and it just essentially bounces around long enough that there's an effective opacity that emerges. This is a completely hypothetical idea. Now, everything probably would have stayed right there in science for all these years if we had not concerned ourselves with the fusion question, right? So what we're going to do next week is we're going to look at how the paradigm shifted from looking at the sun as a material object that was needing an explanation to who cares. What we care about is how it's powered, because if we can figure that out, it's going to be really useful to us here on Earth. And so that's where we get into the ideas of Eddington and Einstein and all of these guys. So let's review the 6 pillars with our last, I guess we have 10 minutes left here. So I want to go through these 6 pillars. This is where modern science stands today. So the first one is Laplace's nebular hypothesis. This was an idea that was established very early, I think end of the 1700s or maybe like right around the turn of the century. And this was based on the idea that there's a big nebula that contracts and forms the sun. This is essentially the idea that we have today. And if you took the last semester's class, you'll see how we actually explored every possibility in between for a couple hundred years and then came back to this idea. Now, what's interesting is that Laplace's his nebular theory, which we now call the solar nebular disk model, is essentially the same idea, and it never really specified which solar phase these materials were in. Now, I've spent a lot of time talking to people, planetary scientists. I have a number of friends who are doing this. I was just down in LA hanging out with some of them. And the question you ask them is, okay, you have these nebulas that are collapsing, right? And they treat them as if they're essentially the same composition. Well, what's the sun made out of? Mostly hydrogen, a little bit of helium. Okay, there's hydrogen and helium that collapses. Well, are there other molecules in these molecular clouds? Are there big, complicated molecules? Yeah, there are. Okay, well, what's the role of those in this process? Well, it's complicated and we ignore them, actually. Which it's like, fair enough, right? You're trying to build these really complicated computer models to explain how this material can gravitationally collapse on itself. But there's a lot of missing variables, particularly the condensed matter variables of it, right? It's much easier to work with a gas than it is to work with complex chemistry. And it turns out there's really complicated molecules in these molecular clouds that are condensing. And we can see some of these solar systems forming. And it's troubling because they look nothing like the way that we explain our own solar system to ourselves. So without getting too much into that, suffice it to say that this nebular disk collapse idea is completely non-specific to the composition of the material composition of the sun. All right, so the next piece in the puzzle was essentially a mathematical treatment of the nebular disk collapse, right? This is a guy named Helmholtz, who was really important in thermodynamics at the time, kind of a super famous dude, who came along and supplied the mathematics necessary for this contractile process to occur that would essentially lead to the heat that was being generated. So the idea is like as these things cool, the density goes down, these things start to collapse on each other. As they get really close, the atoms get close to each other, gravity takes over, they start squishing, there's a lot of pressure, a lot of heat, and this powers the sun, right? This, surprisingly, was the first time that we moved away from the idea that meteors were heating the sun, okay? This is incredible, you know, because this guy was the first person to come along and supply a mechanism for it that didn't require this unobservable phenomena. We didn't see meteors crashing into the sun all the time, but this made a lot of sense. It worked on the previous theory, and this is what you see a lot of times, by the way. Successful scientific theories, the new theories, they incorporate the old ones very nicely, right? If you have a brilliant scientific idea and you want people to care about it, you better be really sure to find a way to integrate all of the knowledge that has come before you and to make the people whose ideas you're displacing not feel displaced. You know, this seems like a political issue, and it is, right? But all of life is. You have to work with other people. This is really important. And honestly, like, you know, you can do that however you want. You can take the best ideas of their ideas and incorporate them into yours and move on. And this is what Helmholtz did. Let's see if I have a quote from Helmholtz. All right, so Helmholtz wrote, "The general attractive force of all matter must impel these masses to approach each other and to condense, so that the nebulous sphere became incessantly smaller, by which, according to mechanical laws, a motion of rotation originally slow, and the existence of which must be assumed, would gradually become quicker and quicker. By centrifugal force, which must act energetically in the neighborhood of the equator of the nebulous sphere, masses could come from time to time to be torn away, which afterwards would continue their courses separately from the main masses, forming themselves into single planets, or similarly to the great original sphere, into planets with satellites and rings, until finally the principal mass condensed itself into a sun." There you have it. That's essentially what we work off of today. This is almost 300 years old. Well, that either means it's a really good idea or nothing better has come along. All right, the next pillar, I'm going to make it through all of these, is the phase state. So people started exploring with high pressures on Earth, right? They started doing these things they call phase diagrams, where you basically put a lot of pressure in and you look at the temperature relationship. Now, the problem was, and the guy who really gets all the credit for this was this dude named Thomas Andrews. Andrews didn't have access to the back half of this diagram in his lifetime. He only had some of these more moderate pressures, and he certainly didn't have these super high temperatures, right? And so Andrews essentially said, look, this thing, at the temperatures that we expect, like the sun is, we can look from the black body spectrum. If we treat the sun as a black body, it's convenient to do that. Then we end up in this plasma region, essentially. What's up?
What's the difference between a solid and a metallic solid, as well as a liquid and a metallic?
Good question. Yeah. So what's interesting is they had no conception of that during Andrews' day. Okay. So the only thing that was available, the only phase of matter that was available in his day was these. They didn't even have a word for it, plasma. They just called it a gas back then, right? I mean, this really put the nail in the coffin of the condensed matter sun, right? It already didn't make sense by density that it should be a solid or liquid body. But, well, solid, let's leave it at solid. Couldn't be a solid body. But they also didn't understand like the density thing, right? Nowadays we say, oh, well, the density in the interior of the sun is something outrageous. I can't bring it to mind right now, but it's unbelievably dense at the center, and it's unbelievably thin at the outside, right? So there's a spread, but you asked the difference between, so these new phases of matter were discovered recently, very recently actually, that if you have tremendous pressures, right, and these are pressures that we should certainly expect in the interior of the sun, and you have sufficient temperature, you end up with these weird phases of matter, right, where liquids actually start to conduct electricity, right, under enough pressure, hydrogen in particular, and actually it's theorized that this kind of hydrogen is at the center of some of our big gas giants, and it's in some part responsible for the generation of the magnetic fields. Jupiter has the biggest magnetic field in the solar system, aside from the sun, right? How does it do that? Well, it needs some sort of metal spinning, right? And we did this last semester. I unfortunately don't have time to explain magnetic fields to you right now, but maybe we'll get to it. And so these phase diagrams at the time, remember, this right-hand side was completely absent to them. They had no idea that it was there. And honestly, I will make a prediction that these phases will come into extreme play in the next century of solar physics. Yes?
Is a metallic liquid the same as a supercritical fluid?
Related, but supercritical fluids are usually cooled. Yeah, they are phase states that are peculiar and only available under certain strange conditions. Yeah. But okay, so the idea that matter has different phases and that when matter is under temperatures and pressures, it can behave strangely is a really old idea, but it's also developed extremely, it's developed a lot since then. Okay. All right, bear with me for a couple more minutes. We already talked about Kirikov's idea of the black body. I'm not going to beat you over the head with that anymore, but needless to say, Kirikov essentially went to his grave arguing that people didn't understand this and they didn't know what was going on. The last line of evidence was this idea that people discovered that when you put gases under pressure, their lines spread out, right? So people started thinking, oh man, if the sun's is full of gas, it's under a lot of pressure, well, maybe you can generate a continuous spectrum if you pile these things up nice enough. The problem is that the spectra that you get from pressure broadening never looks anything like that Planckian black body spectrum. And so next week, we're going to talk about the different mathematical convolutions necessary to hammer pressure broadened spectra into a black body spectra. And we'll see how they do that. And it's going to be a story. We're going to have to do with general relativity. We're going to have to look at the popularizers of that idea. We're going to have to think about why people stopped caring about materials and why they were more concerned with the technological application. Otherwise, if you haven't signed the attendance sheet, please make sure to do it. And I hope you guys have a wonderful weekend. I'll see you guys next week.